Welcome to The Explainer. Today, we're prying open the black box of deep learning. We're going to look past all the hype to see the surprisingly elegant mathematical engine that's really powering this whole AI revolution.
All right, let's just dive right in. The best place to start is with the single biggest idea that separates the AI of today from all the old-school programming that came before. See, it's not about writing smarter rules for the computer to follow. It's about throwing out the rule book completely.
You know, for decades, the main strategy for AI was building these giant knowledge bases. Basically, programmers would try to hand code every possible rule about the world, like, if a thing has pointy ears and whiskers, then it might be a cat. But this was just so brittle, it could never keep up with the real world. Representation learning, the modern approach, just flips that whole idea on its head. Instead of rules, we give a model tons of examples, thousands of cat pictures, and it figures out the important features for itself. It actually learns its own internal concept of what catness is.
So if we're going to build this kind of learning engine, it needs a language it can actually understand. And it turns out that language isn't C++ or Python. Nope, it's pure mathematics.
The first dialect this engine has to speak is linear algebra. You can think of it as the language of structure. It lets us take all this messy, real-world stuff, every pixel in a photograph, every word in a sentence, and translate it into a vector, which is really just a list of numbers. And that vector acts like a coordinate, a single precise point in a huge mathematical space. And that translation, from messy reality to clean math, is the absolute first step for any AI model.
And this is how it all scales up. These simple building blocks, single numbers or scalars, lists of numbers or vectors, and grids of numbers or matrices let us organize enormous amounts of information. An entire data set of thousands of images can become one giant matrix. And this is so powerful because it means we can perform one huge calculation on all of it at the same time. And wouldn't you know it, that's exactly what modern GPUs, the graphics cards and gaming computers, are built to do.
Okay, so turning everything into a neat grid of numbers sounds great, but we all know the world isn't neat. It's messy. It's ambiguous. It's full of uncertainty. So that brings us to the second, absolutely crucial dialect our engine needs to speak.
And that's probability theory, the language of uncertainty. If linear algebra gives our data its shape, its skeleton, then probability is what allows it to reason about things that aren't just black and white. It's what lets a model make an educated guess, to say something like, look, I'm 95% sure this is a cat, but there's a 5% chance it might just be a small dog. This is what makes AI tough enough to actually function out there in the real world.
Okay, so we have the parts and we have the language. Now for the really cool part, the action. How does the engine actually learn? Well, you have to think of it like a journey, a search for the best possible answer.
The first step on any journey is figuring out how lost you are, and we measure that with something called a cost function. Just think of it like a scorekeeper in a game of golf. It looks at the model's predictions and calculates a score for how wrong they are. A high score, a high cost, means the model is way off. A low score means it's getting really close. The entire goal of training an AI is just to find the settings that get this score as low as possible.
Now, I want you to imagine that all the possible settings for our model create this vast, invisible landscape. The height of the ground at any point represents the error or the cost. The model's job is to find the lowest valley in this entire landscape. But here's the catch. It's not a simple bowl. It's this incredibly complex terrain with mountains, flat plateaus, and these really tricky things called saddle points, spots that look like a valley from one direction but a hilltop from another. This is the treacherous world the model has to learn to explore. So how does it find its way? It uses a beautifully simple process called gradient descent. Imagine it standing on that landscape. At every single point, it just calculates the gradient, which is just a fancy word for the steepest direction. And then it takes one small step downhill. And it just does this over and over and over. A tiny step, then another, slowly feeling its way down the error landscape. And that slow, patient, downhill walk, well, that's the essence of learning.
But here's the twist. There is such a thing as being too good at this game. Sometimes, the engine gets so good at navigating that specific landscape that it learns the path perfectly. And believe it or not, that perfection is a huge, huge problem.
It's a problem called overfitting. And it happens when a model stops learning the general patterns and instead starts to just memorize the specific examples you showed it. It's like a student who memorizes every answer on the practice test but doesn't actually understand the subject.
They'll ace the practice test, but when they see new questions on the final exam, they completely fall apart. That disconnect between doing well in practice and failing in the real world is called the generalization gap.
So how do we fix this? Well, we use techniques called regularization. You can think of them as guardrails, or maybe a kind of penalty, that stops the model from getting too complex and just memorizing everything. It's a trade-off, for sure. We're actually willing to accept a slightly worse score on the training data in exchange for a much better performance out in the real world. It forces the model to find the simpler, more general solution. All right, let's zoom out for a second. This incredibly powerful learning engine, it wasn't built overnight. Not even close. It's actually the result of decades of research, full of incredible excitement, followed by long, cold winters of total disillusionment.
The story really happened in 3 waves. The first was cybernetics, back in the 40s to the 60s. The ideas were amazing, inspired by the human brain, but they just smashed into a wall. Computers were way too weak. That led to the first AI winter, where funding dried up. Then, in the 80s, we got a second wave, connectionism. It had huge breakthroughs, but it stalled out too, because training really deep networks was just too computationally expensive. Then, around 2006, the third wave, deep learning, finally kicked off. And why now? 2 things changed everything. 1, the internet gave us massive datasets to learn from. And 2, the video game industry gave us powerful GPUs that could finally handle the math. That was the perfect storm.
And that really is the most powerful idea at the heart of this whole thing. By learning its own representations of reality, straight from the data, AI might not just be copying how we think. It might be on the verge of discovering a fundamentally different way of understanding the universe altogether, and that's something to think about.